So we discussed general complex structures, in particular, and how they're used in explaining this relation between non-commutative deformation of the B model and A model. And this differential geometry is explained in the thesis by Marco Gualtieri. So it's online somewhere, so you can Google it. Then the relation between this generalized complex geometry and sigma models. In my papers, from 2003 and 2005. And this is all related to deformation quantization, but as I just mentioned now, one can extend this to get some version of geometric quantization as well. That's in the paper by Branes and geometric quantization. It's by Gukov-Witten. As you can see, it's all pretty old story by now, just 10 years old. Okay, so that's as far as references are concerned. Well, now let me make some remarks on the previous discussion. So first of all, I explained that non-commutative. So if you have non-commutative deformation of the B model and the corresponding derived category coherent sheaves, then you can also identify that in the case when this Poisson structure is inverse of the complex symplectic form, you can also identify it with the, you can also get it from A model with the B field. But this actually, since maybe a bit unfamiliar, maybe I should say that in some cases you can just drop that B field and still get the same thing. So this is the case. Okay, anyway, let me just say so. So with the complex structure and Poisson bivection related to A model with B field. Which a B field in this case is simply some close to form on our manifold. So target space, right? But
this is when P is non-degenerate.
This is the case when since omega inverse B is supposed to be complex structure, B is not degenerate. That's a special, so in the case when, maybe I should say the other way around. So if in the case when omega inverse B is almost complex structure. So now in some cases actually this is the same as A model without any B, with zero B field. So if cohomology class of B is 0, can the A model with B field is equivalent to the usual A model.
Do you change symplectic variety?
Sorry?
When you say this, you start with some symplectic variety.
Yeah, so you have symplectic. So in general, in physics, when you define A model, you have a complex symplectic variety plus a closed two form.
Yes.
But if cohomology class with two form is trivial, it's clear physically that it's just equivalent to.
It's the same symplectic variety. You don't change.
Yeah, no.
So this was my question.
Yeah. So it's just on the same with the same targets. So it's kind of trivial property. More general actually.
So to define such equivalence, you have to pick a form whose differential is B?
Yeah, right. So more generally, if I'll write it this way. So if it has integral periods, then, well, 2 pi times integer, then it's still equivalent to the usual A model.
But already non-trivial.
Sorry?
But this is already non-trivial.
Well, it's kind of, they're both kind of the same.
So then you have to pick a line bundle with
Yes.
a connection whose curvature.
Right. So now, and what it means is that, remember, in the case when we thought about this A model with a B field, we our basic brane was this quadratropic submanifold, just the whole target space manifold with trivial connection on a trivial bundle.
Could you put this
And here, so we just need to start with this. We just use under this equivalence, our sort of trivial quadratropic brane goes to one with the non-trivial gauge field, namely the one which sort of trivializes this class. Yes, yeah. So, and that's actually originally this was stated, like in our paper with Witten on geometric Lagrange, that's how we used it, this statement. So in this case, so the trivial quadratropic brane is replaced with this what's called canonical quadratropic. Namely the one which carries some, you need to choose some line bundle with a connection whose curvature satisfies the same condition as that B. Okay. So actually, well, in some cases F is just cohomologically trivial, but anyway, so that corresponds to this case. Sometimes it's not, depends on the particular example. So another remark. So that's why on our paper, say with Witten, we didn't talk about B field much, because usually, our B was actually trivial in most cases, so we could just use this move and use this brane with non-zero, non-trivial connection with curvature. The second remark is that relates to emergence of a geometric quantization. In that case, one needs to not just find an algebra, non-commutative algebra, which quantizes the algebra function on a manifold, but actually find some module over it, and moreover, this module should have some Hilbert space structure. So how is it done? So to get modules, can pick any Lagrangian A-brane, and it's kind of easier to do in this language when you in the case when B satisfies this condition. Sorry, it's a Lagrangian submanifold. Well, let's suppose when.
Lagrange binomial satisfies which condition?
So in the case when there's B there, so you want it's Lagrangian submanifold on which B restricts to trivially. So, or here you can just if you use this formulation, then you just have the usual Lagrangian submanifold. There's no B. Okay, so. Nevertheless, it's kind of difficult to figure out what this module structure is, except in the case when this Lagrangian is actually complex Lagrangian submanifold in this complex structure. So in any case, if you pick the Lagrangian, how to get a module? Well, just consider, remember, so to get an algebra, consider it vector space attached to an interval with the same boundary conditions, and then this kind of Bordisms show you that the space of states attached to an interval with this boundary condition gives an algebra of some sort. If you get a module structure, you just draw the same diagram, but pick this other boundary condition just on this part of the boundary, and the same diagrams show that this vector space attached to interval with boundary conditions alpha and beta is acted upon by this one, by the algebra. So and well, that's not just a module. How to get Hilbert space structure? Well, it turns out, as explained in this paper of Gukov and Witten, it's sufficient to do the following. It's probably also necessary to choose to get Hilbert space structure.
But still, I see that it shows that F, but how do you describe the space before? How do you describe the space?
Well, okay. So the space. Suppose we're in a situation where this is the easiest one, namely when the A brane is a complex Lagrangian with respect to the complex symmetric form. Then this space attached to an interval, well, you have some, say, submanifold, like, say, symplectic manifold X. Well, it's complex symplectic one, right? Omega, such that, so imaginary part of this symplectic form omega. So omega is closed to form type 2, 0. And it's holomorphic and degenerate. And an imaginary part but is this our symplectic form used to construct the A model. Yes. And then, so the real part of this guy is precisely that F. And the ratio is the complex structure. So, so in that case, and we're picking the submanifold Y in X. Yeah. Okay. So like now Y in X, complex Lagrangian. Perhaps with some line bundle. Well, let's forget about the line bundle. Then, okay, maybe put a line bundle here. Well, okay, it's the line.
F is what you called B before, or is it?
Well, see, I use this picture where I limited B in favor of a non-trivial line bundle on my space-filling brane. Like. So, basically to make contact with this paper, Book von Witten, which always do that. They sort of eliminate B in favor of a gauge field. So, in this case, that space is just Dolbocca homology of Y in K, well, square root of canonical class of Y, tensor restriction of that bundle here. Okay, so we have this. We need to really to choose some line bundle on X whose curvature with a connection whose curvature is this, and you need to put it here. Restriction to X to Y. Sorry. So it's the space on which this thing acts. And in many cases, we just can just.
Sorry, how is it related to alpha and beta?
Well, alpha is a cosotropic brane, which is a space filling,
Okay.
and beta is this complex Lagrangian with. Yeah, in general, when you you might not have a spin structure on this manifold, and then you don't have this square root. Then just need to replace this square root by this spin structure by spin C structure.
Okay.
So, and actually, if there's no spin C structure, then actually a brane actually doesn't even exist. So this is what's next condition for existence of a brane is existence of spin structure. Okay. So now what about Hilbert space structure? Well, to get that, you need additional constraints. And the well, I'm not sure how general this is, but one thing which I think it's pretty general what they say is that so yeah, actually let me so to get Hilbert space structure, need an involution on X
complex or anti? Harmonic or anti?
well, it's really an A model thing.
Yeah, okay.
So,
Sorry. But you use complex structure to define the
well,
homology.
right. So, so the condition really is this one that something like that. So it's equivalence of the it establishes equivalence between A model with symmetric form omega and minus omega. So then you can define Hilbert space structure on that space alpha beta. So I won't discuss this because for me it's not terribly important. But that's how geometric quantization enters the picture. You need to impose additional constraints.
How does it act on F?
My question is, your variety is not compact. So when you find Hilbert structure, then you want to integrate over Y. There's no other way.
Well,
You can imagine describing Hilbert structure. So why would the integral converge?
let's see.
You probably
Yeah, probably needs to take out two sections in the end. So
Okay.
yeah, so there's a this sort of pre-Hilbert space structure really. Okay, yeah.
And how does tau act on F?
Yeah, so I think again in a good situation, I think it's supposed to preserve it. So you want, yeah. So you actually to get, okay. Sorry, take it back. So you should also the condition like that.
So
Because
then it's anti-holomorphic.
yeah, then it's anti-holomorphic. Yeah, right. Right, because I also want to preserve the brane, so the brane should go to itself. So anyway, okay, so that's the story of how to get deformation quantization and even geometric quantization out of some A model with target this complex symplectic manifold. Now I would like to now go higher in dimensions because in the physics literature there are a number of situations where deformation quantization arises, and in many cases it doesn't seem to be related to this story. And I want to explain that there are two cases actually, and one of them is related to this story, even though it appears to come from higher dimensional field theory, like 3 or 4 dimensional. And there's another one which doesn't seem to come from related to this story. Well, it's some deformation quantization again, but it's more. It makes sense really when, okay, so this story makes sense when the target space is a non-singular complex symplectic manifold, or maybe hyperkähler manifold. You can ask, well, what about singular case? Suppose you have some hyperkähler cone or something like that. Well, I don't know how to generalize this story to that case. However, when there's a conical situation, there's another way to produce deformation quantization with some remarkable properties, and I will discuss it later. I don't know whether it's related to this story. So anyway, so there's another way to get the same thing, which in the end turns out to be equivalent. So, and that way goes through 3-dimensional field theory. So namely, when you have a complex symplectic manifold, there's another thing you can do. Natural thing to do is to attach it to a 3-dimensional topological field theory. Remember, so when you have real symplectic manifold, natural thing is to attach an A model, which is 2-dimensional field theory. But when you have complex symplectic manifold, natural thing is to get something called Rosansky-Witten theory. So this theory is kind of 3-dimensional analog of the B model. So it's more complicated than the A model, but than the B model, but less complicated than the A model in some sense, because in both, just for the B model, your path integral localizes to constant maps. So in the end, everything reduces to integral. Oh, you have some basically maps. Have maps. You sort of integrate over maps from M, which is 3-dimensional manifold, oriented 3-dimensional manifold, to this X. But in the end, everything localizes to constant maps. So in then all your correlators reduce to some integrals over X. So, but unlike the B model, this is non-trivial perturbation theory here. So it's perturbative theory, so one can actually, in perturbation actually is convergent because you can show that for any given correlator, it's actually, Feynman diagram sort of becomes 0 after when it gets actually complicated. But so if you have convergent perturbation theory, but it's non-trivial perturbation theory, unlike in the B model where you don't need to do any perturbation theory at all, just zeroth order gives you the exact answer. So it's a bit more non-trivial theory. Anyway, so let me state some things about this topological field theory. So first of all, when you have 3D topological field theory, it attaches a number to a closed 3D manifold. So you have some closed 3D manifold. Then, well, I cannot draw it, but it's closed in 3D, so it attaches a number called the partition function. And when you have a closed 2D manifold, which is a vector space. And when you have a one-dimensional manifold, closed manifold, which is really, you can just reduce the case of circle, let's just do it braided monoidal category. Now, all these things have some additional structure. Well, I already said what the structure is here. So this is a braided monoidal category with some additional properties. Well, it's pretty non-trivial to determine what it is. Well, let me just say that this is also pretty hard. So let me just say some simple things. So first of all, when your sigma is just a two-sphere, then the vector space is simply cohomology, double cohomology of, well, shift cohomology of OX. Actually, here's all non-singular. So by the way, since it's double cohomology. So and on the hand, another example. Well, this is a thing which is kind of difficult to understand. So this category attached to a circle is actually some sort of Z2 graded version of the derived category of coherent sheaves on X. We have like two periodic complexes of say, coherent sheaves, and then you form sort of derived category from that, but with some non-trivial monoidal structure. So it's braided monoidal structure. It's not the usual one, which is symmetric. It's braided. There's non-trivial braiding. And if you're interested in some explicit formulas, you can check out paper by Roberts and Sewan.
Is it symmetric or only braided?
Sorry?
Is the category symmetric or only braided?
It's only braided. And that precisely comes from this non-trivial perturbation theory. So, so if you think about this omega as something which relates to quantization, so its inverse is really what should enter various. So, you can imagine that omega is rescaled by a factor of like this, omega over h bar. And when its inverse is going to enter in various perturbative computations, therefore you're going to have powers of h, positive powers of h bar. And it turns out that the associator here is non-trivial, and the braiding is non-trivial, and they appear at order h bar, precisely. So you sort of take the limit when h bar is very small, that is, you blow up this symplectic form and take it to infinity, then this associator and the braiding become trivial. But that only happens in the limit. So, but I'm not going to focus on this. I want to let me just say, look at this one. So this is actually an algebra. It's actually not in any dimensions. If you look at TQFT in any dimensions, then if you look at the vector space attached to n-1 dimensional sphere, if you dimension n, it's always a commutative algebra. But it actually has also additional operation. It's a
Does it have to be commutative?
when n is greater than 1, it has to be commutative, but has some extra structure because it's a really En algebra. And let me just mention that. So as an algebra, this is just take the usual commutative algebra structure. However, there's an additional operation on this algebra. It's really a Gersten-Haber algebra. Well, not sorry. It's a Poisson bracket there. It's a Poisson algebra. So V over S2 in this case actually is a Poisson algebra, and that's true in any three-dimensional TQFT. By the way, there's always a bracket, Poisson bracket there. The way it's defined is interesting. So abstractly, so let's see. So in this topological field theory, the way it's defined, there is some Beresty operator that's called Q, which acts on pre-observables, and observables are really Beresty cohomology classes. So observables, topological observables, are Beresty cohomology classes. So what do I mean by this? Well, there's some on the space, formally on the space, but it's not really space of maps, but some supermanifolds whose bosonic part is the space of maps. There is some vector field which is odd and squares to 0. Its Lie bracket of itself is 0. That's called Beresty charge. And observables are just functions on this infinite dimensional space of maps, well, or on the supermanifold, whose bosonic part is this, annihilated by this vector field. And the ones which are themselves, so you have some observable, some function annihilated by this guy, then f is trivial if f is itself obtained by acting by this vector field, which is called q on some other function. So now, interestingly, you can so typical typical observer will be some really some function on x, and then use this map to pull it back to m and evaluate at some point on m. But turns out it doesn't matter at which point you evaluate, because sort of moving on m doesn't really change the cohomology class of the operator. The way it happens is that suppose m, so let m be just flat, just R3. Well, in this case, turns out that well, that moving here is done using momentum operators, translation operators. It turns out that there are 3 of them, and turns out they all Beresty exact. There's some other odd guy for each direction on R3, such that pi is a Beresty is well, anticommutator, so like this. So, in particular, if you start with some, so these guys really form a fermionic 1 form on M, which is flat on this case. So starting from F, you can get 1 form by, it's called F1I, simply by taking letting Gi act on F. And that's called the first descendant. And then, in fact, again, get a 2 form on M, defined like this. It's just Gi, Dj, and F, Dxi, Dxj. So, and abstractly, this Poisson bracket is defined like this. Oh, it's yeah, so I would just take, say, so what's the bracket of 2 observables? Well, I'll take G evaluated at point 0, say on R3, multiply by F 2, that gives me a 2 form on R3, and then integrate this 2 form on a sphere centered at 0. So this gives you a new observable, and that observable is by definition the Poisson bracket of F and G.
What does the Beresty comes from maps?
Well, that's how topological filter is defined. So observables are, so you have some supermanifold of, well, some supermanifold defined using maps from M3 to target, and then on that supermanifold you must.
How do you write that Poisson structure in
Yeah.
How do you write it?
Yeah. Now in this is particularly abstract. That's true in any 3-dimensional topological field theory, but in this particular case, or Witten theory, this is an obvious candidate. Let's say if you look at degree 0 cohomology, degree 0 part of this, then of course there's just homomorphic functions. There's a natural Poisson bracket there coming from this inverse of the symplectic form here. And if you actually go ahead and compute, you'll find indeed that in this abstract construction specializes, you get that this abstract guy is simply Poisson bracket with respect to the inverse of omega. Okay. Yes?
So Q is somehow coming from the action function?
The action function actually constructed using Q. So the way it's done, you start with supermanifold with a Q. That's your, there's something called a KSZ construction. That's your starting point. Your supermanifold.
AKZ means some volume form.
Yeah, that symplectic structure takes care of that. You get some volume form from that.
Space issue.
Yeah, but you can construct it using this. That supermanifold is such that you get volume form out of symplectic form on the target.
Well, example which I would like to understand is when X is the orbit in the algebra, or to the algebra, without the case, then essentially we know the quantization, then the canonical invariance of the
Yeah.
So the quantization should give you representation. If you start with compact group, so you will essentially get finite dimensional representation.
Yeah.
But I don't see any Poisson structure.
No, I mean,
It could be zero, which is
We have
possible,
caten- no, we don't have. We have okay. In this case, in the Raskowitz case, Poisson structure is always invertible, so it's always there. It's in the symplectic form. Anyway, so
So what happens if X is just C2 with the constant symplectic structure, dx dy? Is it possible to say what this braided category is?
in that case, it's trivial. A trivial deformation. There's no. So you get a trivial deformation. Like the correction to the associator or braiding, say to the braiding, is proportional to the for two objects. Suppose you want to braid two objects, proportional to the Tia classes of these two, say, coherent sheaves. So times inverse of omega somehow. So you don't get anything if you target space.
So you can't resolve the category theory in sheaves of nights, right?
Yes. So you can look up these formulas and say Justin Roberts and so say one paper. They're quite explicit about how to construct this associator. Anyway, so the point is that okay, so Rosansky-Witten theory gives you naturally commutative algebra with Poisson bracket, and that's the vector space. This comes from vector space attached to a two-sphere, which is a natural basic object for the three-dimensional field theory proposes to consider. But since we want to have a non-commutative deformation, can we get that too from the Rosansky-Witten theory? So now, of course, it turns out there is one, but you need somehow to let me explain how to do it using this what we know from the previous lecture, namely that a model under suitable circumstances gives rise to non-commutative algebras. So okay, let me see. So suppose you do the following thing. So consider the case when, so let M3 be something two-dimensional times S1. So in that case, on physical grounds, they should reduce to two-dimensional topological filter and sigma. So which one is it? Well, it's not hard to convince yourself. In this case, get B model with target, same target, X. And it's, of course, a Calabi-Yau manifold simply because it's complex symplectic to begin with. But other than that, the symplectic form doesn't really matter for this B model. Now, how we would like to get non-commutative deformation of this, okay? And how do we do that? Well, for that we need to modify this procedure. We still can take, so instead consider the same guy, but let's consider a different BRST operator. There is a vector, well, some infinite dimensional, it's a super vector field, odd vector field which squares to 0 on the, some odd vector field on this infinite dimensional space of maps from here to X. We consider the following one, called Qt because it depends on the parameter. So I call the coordinate along here x3. So in the three-dimensional case, when you have flat situation, you have three additional supersymmetries which satisfy this property. In our case, only one direction has a flat metric, namely S1. So only one guy which you can use, namely G3. And if you use it to modify that Beresty operator, that's a good Beresty operator from two-dimensional viewpoint. Its square, though, is not 0. It's its property, it's the translation along this circle. But anyway, all observables are independent of position anywhere, including here, so it doesn't really matter. So you still get the topological field theory in two-dimensional sense. So if your observables are extreme dependent. So, okay, so you get some other TQFT out of this, which depends on the parameter and reduces to the B model when t is 0. So which topological field theory is it? The 2D TQFT is a B model with target X deformed by Poisson bivector, which is T omega inverse. Okay. So, or by the, you can also think there's a model in this case with some B field by the previous result. So one can actually check this by direct computations. So, okay. Now, and we know that in this theory, two-dimensional theory, there is some special brane, which, depending situation, we call it trivial quasitropic brane, a canonical quasitropic brane. So called trivial one. Suppose it's an A model with a B field, and we just take the trivial gauge field on our space-filling brane on X, and then it's endomorphism algebra turns out to be non-commutative deformation of the algebra of holomorphic functions. So can we explain that in three-dimensional terms? So, from the 2D viewpoint, a brane is simply a boundary condition for the two-dimensional model. So that is, we do this some interval and put some boundary condition here. If you put the same one there, you're going to get this deformed algebra. So what does it look like from the point of three-dimensional viewpoint? Well, in 3 dimensions, remember, we have a circle, invisible circle fibered over every point of this guy. So it's really should be 1 times S1. So it's really a cylinder. And when invent some boundary condition on this side, both sides, so that which reproduces this quasitropic brane when we sort of forget about the circle, the Kaluza-Klein reduction. Well, it's a completely canonical object, right? So in this two-dimensional field theory, because we didn't make any choices, we just you chose this parameter. Should be canonical boundary condition for this 3D theory as well. Well, easy to guess what it should be. Just cap off the cylinder with 2 hemispheres. Okay. So basically just S2. So the claim is take S2, but so I use Beresty operator, which looks like this. Then the resulting space of states is going to be have an algebra structure, which is non-commutative deformation of the algebra of homomorphic functions on this manifold X. So what happens with this? Well, of course, what happens at this endpoints? Well, if you we can generalize this deformation in the case when our manifold not just well, not a product, but we can just imagine that we do something like this. We pick a vector field here, which looks like this in the interior, but of course has zeros at these 2 points. So we take S2, take a vector field which is sort of runs along the parallels of the sphere, and we define QT to be simply Q times T V mu G mu. where the mu is chosen vector field in a sphere which runs along the parallels. And this is the and provides another deformation of the this is a sort of modified version of the Rosansky-Witten theory on S2 times time. So we look at the cohomology of this guy. In the cohomology of this guy, we expect to have a non-commutative algebra structure. Unlike the case when if you drop that, the cohomology is going to be just algebra of holomorphic functions, but with this guy, it's going to be commutative deformation along this bivector. And that can actually shown to be the case. So that's going to be a generic way to get. You can do it directly in 3 dimensions, but you can also explain it this way. Simply, you need to observe that this deformation.
Usually Poisson structure of the relative fact that you deform your commutative algebra to non-commutative.
Yeah.
Then in first order you have Poisson structure. If the Poisson structure we described before comes from this kind of deformation, or is independent structure?
So we start with 3-dimensional field theory, which is some special, which by definition involves depends on the choice of a symplectic homomorphic symplectic form. So and when you reduce in this deformed way, that is, look at the cohomology of this deformed operator, then the resulting space of states has a natural structure of an algebra, which is non-commutative.
Deform when t is 0 you have commutative.
Yeah.
Now you have family algebra.
Yeah.
Then in first order it gives you Poisson structure.
Right.
On it's the same Poisson.
Yeah, it's the same one. Yeah. Yeah. Right. So that's a computation, and so I don't have time to go in detail for this. So if you're interested, this is explained in these 2 papers. Well, so by Yagi. So he explains in detail what it means to deform Rosansky-Witten theory by modifying the Beresty operator like that. And the fact that canonical casotropic brane corresponds to this capping off the cylinder, it's explained in a paper by Nekrasov and Witten. Like 4 years earlier, so it's kind of illogical time of events. We'd like to use the time machine. But the point is that the Nekrasov-Witten arguments kind of roundabout. So this paper sort of cleaned up lots of arguments by embedding into Rosansky-Witten theory. So they don't use language of Rosansky-Witten theory here. So it's a bit difficult to see the connection. But anyway, so okay, so so you can see that this. So now, if you look at the physics literature, there are a number of situations where physicists encounter deformation quantization of either deformation quantization of some algebra of functions on a holomorphic symplectic manifold, or maybe modulo over that deformation quantization. So let me in all cases you can explain this in terms of this construction. Okay, let me explain it a bit differently. So consider 3-dimensional field theory on R3. So for now, non-topological. Take supersymmetric field. Rosansky-Witten theory comes from a supersymmetric field theory. Okay, so actually let's a bit backtrack. The most interesting case in some sense is when this target space is actually hyperkähler. So then Rosansky-Witten theory is just a twist of a supersymmetric theory. So you can use the language of supersymmetric theory to begin with. So there's suppose X omega is really hyperkähler. So actually there's a whole sphere, 2 spheres of complex structures, but I'm focusing on one of them. So consider a 3-manifold of this form. And it's a flat situation, and I'm going to consider, so in this case, I can consider deformed Beresty operator of this form. something like that. So, so this vector field has a 0 at origin, and for an operator to be invariant under this guy, it has to sit at the origin and satisfy some additional constraint. So in this theory, then, if you don't have this,
Coordinate on R is the coordinate on C? What is
t is just a parameter, just like there.
T is a parameter. And Z
So here's the coordinate z, and here's the parameter, no, say, maybe tau, time is going to be tau. We'll use t for something else. So not everything is translation invariant in R. So just look at this Bresti operator, and what it does is, first of all, essentially reduces the theory to being one-dimensional. Why? Because everything which is Bresti invariant has to actually sit at the origin of this plane, and in addition, satisfy some additional constraint killed by Q. And so in effect, you reduce to one-dimensional topological field as a quantum mechanics. And the algebra observables in this reduced theory is just an algebra, but it can be non-commutative. And turns out it is non-commutative. Namely, it's this computation, you can do the computation and show that just deformation quantization of the algebra of functions on your x along the bivector which I wrote here. So, okay.
It's here is essential that in fact that you're working with a three-dimensional theory, which is not topological. So you don't do
Not really, because I didn't really use anything here. The fact that it's okay, I could.
But
Okay.
when you write the C with GC, that's simple to use topological.
No, I mean not really. No, I can use. It wasn't terribly important that it's hyperkähler. It's just that the theory is nice. It's a twist of unitary theory, so some additional properties hold, except with hyperkähler case. The fact that it's hyperkähler means that I can actually change the complex structure here and symplectic form simultaneously. I didn't really use this freedom. Okay. So let me just say that various observations of appearance of differential quantization can be interpreted in these three-dimensional terms. So some examples are say Nekrasov and Shadashvili. And also Ito, Okuda, and Taki. And then Gayoto, Moore, Netske. So these papers are about one topic and this is about another one. So, but in both can be reduced to some three-dimensional computation. So if you look at actually these papers, they involve four-dimensional gauge theories. Four-dimensional gauge theories. But the point is that in the end, they always reduce in a circle. And they end up with some three-dimensional field theories, which are more twisted and equivalent to Rosansky-Witten theory with some deformation. So, well, they consider a variety of examples. I'm going to focus on go through them. But in the end, you can always reduce to the statement about Rosansky-Witten theory, because all these theories they consider four-dimensional theories in a circle. So the kind of manifolds which occur, well, depends on what you start in 4 dimensions. But for example, you can get say modular space of flat connection on some Riemann surface, maybe with punctures. That's in the Gayoto-Murnetsky paper. Or you can get modular space of Higgs bundles. That's Nekrasov-Shotashvili. So there are different complex structures which appear for the same space. But I don't want to talk about that. Being 10 minutes, I want to describe a more mysterious story, which is also more recent, more mysterious and more recent. So this whole story with Rosansky-Witten theory or the A model in 2 dimensions always assume that you have some smooth complex symplectic manifold. Now another interesting situation is when you have a complex symplectic cone or hyperkähler cone. And suppose I do have hyperkähler cone, because it's the most this is the situation where it is important to have hyperkähler structure. So suppose X is a hyperkähler a manifold with some sort of cone, right? Such like typical examples would be, say, maybe a nilpotent cone of the Lie algebra. So
does it have to have symplectic resolution?
no, it doesn't have to be. So such things appear also in physics, but you cannot define, say, Rosansky-Witten theory with this target or A model with this target. It doesn't make any sense. However, you can embed them into another context called the three-dimensional superconformal field theory.
So what exactly does it mean, hyperconic cone? Is there
Well, in practice, like how to get this three-dimensional superconformal field theories. So you start with some group and some representation R of the group. So the amount of supersymmetry is called n equals 4, or 8 supercharges.
and you do hyperconic reduction? Yeah?
Actually, two things you can do. You can either start with like the T star of R or something like that, and do hyperkähler reduction. Oh, sorry, of R in that representation, which is complex representation. Do like do hyperkähler reduction. Look at the compute the moment map, and take the inverse of 0 and quotient by the group. Or, and that's called the Higgs branch. Construction. Well, and then there's a more mysterious one. The Coulomb branch. So sometimes we know how to compute this. Physicists know if there's sort of three-dimensional mirror is known. So three-dimensional mirror symmetry is equivalent between superconformal field theories, which exchanges Higgs and Coulomb branches. For some cases, we do know that description. Then you can identify the Coulomb branch of this theory with the Higgs branch of the mirror. Sometimes we don't know the mirror, so there should be some other way to do it. And in many cases, this has been computed. Like if the group is abelian, just a bunch of U1s, then it is known how to compute this. And we can ask now, can we see in physics some non-commutative deformation of the algebra of holomorphic functions here? Turns out that you can, and for lack of time, I cannot explain it in any detail, but let me just give you a reference and explain what you can get out of superconformal symmetry, something pretty remarkable. So, so the basic paper in this subject is this one. And then we just sets up this formalism of explaining how to get deformation quantization out of such a superconformal field theory in kind of a canonical way. And that's rather generic, right?
Of which algebra?
Of holomorphic functions on this hyperkähler cone in some particular complex structure. Now, in that case, by the way, there's always a symmetry which rotates complex structures, so it doesn't matter which one you choose. So that symmetry is just part of superconformal symmetry. So, and then they set up the formalism and they computed it in determined some cases simply by symmetries, more or less. And then there are two follow-up papers which actually proposed way to compute this, how to compute this thing. Let's see. Which are more recent by other authors. I won't write them down, but here's the numbers. And so as you can see, the last one just came out like last month. So so this paper does the Higgs branch, which is easier because we know what it is on the classical level, and the other one does the Coulomb branch. The claim is this. There is one parameter canonical deformation of the algebra of holomorphic functions, these cones, which has some remarkable properties which are not obvious if you just think about deformation quantization modulo usual equivalence. I mean, in other words, with deformation quantization, which is special, it depends on just one parameter, no matter what. Usually, if you just think abstractly, there are lots of. If you do resolution first, the H2 of this resolution tells you the space possible deformations. But this particular deformation coming from superconformal theory just has one parameter, regardless of the dimension of that.
Now maybe with mentioning Kajima somehow this definition of Coulomb branch which always comes with canonical quantization.
Okay, so maybe it's related. So the canonical quantization, well, is just one parameter.
Yes.
Yeah, and that moreover, so you can think of it this way. So there's some deformation quantization, there's some special one, and moreover, there's special basis in deformation quantization with some remarkable properties. And that's
Which is the basis of the algebra.
yeah, in the basis in the algebra. And the existence of this basis follows from superconformal. The fact that you have this deformation quantization is some subsector of a unitary superconformal field theory. So I'll just tell you what the properties are and then stop here.
And this basis of which is defined by Generalized. So any R?
Any R. It doesn't matter. Actually, for the properties of this, it doesn't even matter that you start with this superconformal field theory. Just some abstract superconformal field theory. And you always get some. That just unitarity of the superconformal field theory ensures that there is some interesting basis. Okay. Of course, but in general, you don't know how to identify it with deformation quantization of something. Just some non-commutative algebra with the preferred basis. Okay. So you need to pick some G and R to actually think of this algebra as deformation quantization of something concrete. So let me just say, first of all, what is the trick? Why? So in this case, you cannot define like Rosansky-Witten theory or anything like that because you have singular target space. But you can do the following thing, just abstractly. You have superconformal symmetries. You can try to define. Oh, another thing. So the parameter of deformation, in the previous case, it was I thought of it as a parameter in CP1, but here I'm going to think of the parameter in C star. So that's a natural thing to do. So the point is that you can focus on some subalgebra of the sector of the theory, which is annihilated by two special generators in the superconformal algebra. They're both odd, and so the most trivial choice to choose just a couple of supercommuting supersymmetries. So that always exists, and that gives what's called the chiral ring, just the usual homomorphic function, this hyperkähler cone. But we want to do something else. We want to look at sort of homology of deformed operators. And there, so we define some algebra, which is some deformation, and the deformation is like this. So in superconformal algebra, what do we have there? Well, if you look at the usual conformal algebra, so there are, of course, translations and rotations, but also sort of dual, generally dual to translations, called conformal boosts. And there's also important operator called the dimension, just sort of. So one of the elements of the conformal group is just rescalings of all coordinates. So its eigenvalue is called dimension of some operator. So in unitary theory, this dimension is always positive, which is kind of important, or non-negative. That's important. So and then you can classify other generators in your algebra simply by the dimension, particularly. So say translations have dimension 1. Their duals have dimension -1, conformal boosts. And then supersymmetries have dimension 1/2, while the dual one has dimension -1/2. So they're odd. So and what the trick is to deform the usual supersymmetries by adding these superconformal boosts, like that, and some special linear combination. And it just so happens we need to use inverse of this zeta parameter. So zeta lives in C star. So this operator lives in some subalgebra, the full superconformal Lie algebra. So once they're all equivalent, you can also rotate these subalgebras to each other by symmetry. So it's completely canonical except for this choice of this parameter in C star. Okay. And turns out, okay, so the properties of this operator are such that cohomology of this operator, anything which is invariant which is annihilated by these Q's, both of them, must actually sit. So you have three-dimensional space, but again, everything really sits at the origin. Or if you think of the space as, again, as R times C, everything sits again at the origin of C. Just like in the previous case, which I explained. But the starting point is a bit different. I'm assuming that you have superconformal symmetry. And again, for the same reason, if you look at, observable set here, so they can be anywhere on in the time direction. And again, you can show that when you collide these insertions together, there's no singularity, so there's an algebra structure. But of course, there's no symmetry. We cannot exchange the orders to get in general, some non-commutative algebra. So that non-commutative algebra turns out to be some canonical, up to choice of this zeta, deformation of the algebra functions on this cone. Yeah, actually two versions of this. One sort of gives you Higgs branch deformation, another one Coulomb branch deformation. Yes. Yes, question?
And it's like the canonical self-opposite.
That's what?
Like the canonical self-opposite quantization.
Yeah, so let me just say what the properties of this quantization is, because the fact that it comes from unitary superconformal theory tells you a lot about this different. The point is this: you can first of all so you can there's a grading here. So this algebra that we get can be graded by integers, and actually by positive, non-negative integers. This grading simply comes from this scaling symmetry. So you have dilatation in the theory, like dilation of all coordinates, and that what's called the dimension eigenvalue with respect to that dilation is called dimension of some particular element in the algebra, and you diagonalize that. So this is the eigenvalue. Crucial point in unitary theory, it's positive, it's non-negative, and the only guy with zero dimension is just identity operator. So A0 is just complex numbers. So moreover, okay, so the algebra is not graded because this zeta has dimension. It has dimension.
Do you want to
I guess.
the cone branch is a cone, or because that's not always the case?
No, they're not equivalent.
I mean, do you want to assume that the cone branch is a cone?
A cone? Yeah, well, yeah. In superconformal theory, it will be a cone. It's a superconformal situation.
So, for example, if R is equal to 0, it's also superconformal.
Sorry, what?
If your representation is 0, the theory is not superconformal.
But then there's no superconformal theory, which underlies the gauge theory. So let me put it this way. So you can deform this construction, by the way, by resolving your singularity. There's a way, actually in these papers, these two later papers I give reference to, explain how you can do that. But then you lose superconformal symmetry and don't have this nice basis anymore. As far as I could understand. Sorry? It's already deformed algebra. Well, it's really filtered, but the point is this. If you look at, the point is that zeta has some dimension too. So as a result, you have a very particular selection rule. So if you multiply some elements from degree p and degree q, then that's going to sit here.
That's an extremely non-trivial statement that such grading exists.
Yes, that's a very important point. That very non-trivial, but they checked in some example that it exists. And moreover, in this later paper, they actually computed the algebra in a way compatible with this grading. So that's one thing, and there's an additional. So there's further constraints. So there is, if you look at the opposite algebra, it's isomorphic to the algebra with the reversed parameter zeta. It's called even quantization. And furthermore, there is some unitarity constraint, namely there is some antilinear map and some.
Anything psi equals 0, on your right.
Sorry? Say what?
Do you have zeta or not?
Here?
Yeah.
Yeah, there's zeta here.
But you said it holds only for some particular quantization of this core, not for all quantizations.
No, it's just some particular quantization, or maybe one parameter of a quantization, because zeta is this.
So,
parameter.
for example, if I have a quotient singularity, then presumably it would be just for the Y algebra invariance, yes? Not for
Well, you can check those papers, they actually work out.
No.
No, it's not true. There's several. Okay.
It's all quantization schemic.
Okay, let's
Anyway, so the point is that if just specifying a particular singularity, by the way, doesn't tell you what the quantization is, because the different superconformal field theories may lead to the same, say, Higgs branch. So you can actually do computation in any particular theory with the same Higgs branch. You get maybe different. There may be different values of these parameters, for which there is a distinguished basis. So well, yeah, there's some also unitary constraint, which has there's some map like this, interlinear map, which maybe is a bar, I guess, which and some bilinear form, which is positive definite on this algebra. So which pairs some particular components. I don't remember which one. So anyway, so this is the claim, and it just follows abstractly from some unitary superconformal symmetry that there is a distinguished basis, and then in these two further papers they work out what it is for Higgs branch, and in some cases for Coulomb branch. For Coulomb branch, they really do it only for a case when the group is abelian. So, but they hope to extend the methods to the general case. So the relation of it looks very similar to what we did before, because again, relative Witten theory also deform this diversity operator, but we use a different deformation. The result, nevertheless, is very similar. I'm not sure why. So that remains a mystery. So in this paper by Beam and other guys, there is there's a saying that Beam is thinking about it and going to write something, but he never wrote anything. So if you want to, maybe he knows what the answer is, what the relation is to things, but you need to ask him. So I'll stop here.
Thanks.